Alright, here's our Icp-Oes, or inductively coupled plasma optical emission spectrometer. It's able to take aqueous samples and let you know their composition from all the way to percentage level elements, all the way down to part per billion level elements. It works by taking sample or drawing in sample from this zipper here, through this tubing, through this peristaltic pump, into the back of this nebulizer, which is aspirating sample. I'm going to try and get it. You can see the chamber itself is a little misty, and that's from the aspirated sample traveling around in there. It travels around this cyclonic spray chamber, travels around and up into this elbow, and then into the plasma. Now the plasma looks white because it is 10,000 degrees centigrade in there. The sample itself is got a ton of energy that was just dumped onto it because the plasma is so hot, which excites the individual the individual atoms in the makeup of the aqueous solution. They get all this extra energy and they have to conserve it somehow, so they kick off a photon to deal with all the energy they just got dumped on them. That photon is, the wavelength of that photon is a signature for the parent element. So sodium ions or sodium atoms will only kick off certain wavelengths, and we know what those are. Potassium elements will only kick off certain other wavelengths, and we know what those are, and they're never going to change, so they're always the same wavelengths. The instrument then takes the collected light and shines it onto a grating. The grating it works kind of like a prism to split up the light into its individual wavelengths, and then that is eventually shown onto a CCD, a charge coupled device. The CCD, which is not very exciting, but lives back there, is the equivalent of a really expensive and large chip that you would find that is responsible for taking pictures in like your cell phone. And it's the job of the CCD to count photons for each individual wavelength. So you'll get a result of something like 200 counts per second or 200,000 counts per second. But the idea is you run a set of standards through the instrument, and it says, okay, I see sodium at 10 counts per second, and you say, okay, well, that's our 1 part per billion sodium sample. And then it says, okay, I see sodium at 100 counts per second, and you say, okay, well, that's our 0.1 part per million sodium sample, and so on. And you're able to generate a calibration curve from that, and then run your unknowns and plot them on that curve. The curve that's generated happens to be really, really linear, from percentage levels all the way down to parts per billion levels. So when you calibrate for a sample, you're able to run a huge range through the instrument, and it's able to process waters looking at 20 different elements. In about 45 seconds, it'll let you know your composition and composition of your water, and how much of it goes, and it's able to process them in a very rapid fashion. It's a great little instrument.